Welcome to another episode of Untangling Web3. Now, this is the second part of our two-parter on quantum computing. So, in the previous episode, we gave the 101 introduction to what quantum computing is. So, we talked about all sorts of weird and wonderful things in quantum physics. And today, we're going to go into a bit more of a deep dive in what are the actual applications and impacts of this, right, Alec?
Yeah, so if you did make it through that verbal diarrhea that was Quantum 101 now, I hope it wasn't that bad. What we covered was roughly the high level of what quantum computing actually does, something like the key characteristics. So a quick summary, if you don't understand any of the terms that I'm using now, do recommend going through to that episode, and that will kind of form the basis of what we're going to talk about today, which is what quantum computing actually means for the world and what applications it has, and if it's even possible. So one of the key characteristics was superposition, and this at a high level allows qubits to exist in multiple states simultaneously, and this means that quantum computers can process many possibilities at the same time, and this increases computational power for very specific tasks. Okay, so that's the first thing. And the second big thing is entanglement, and this links qubits in such a way that one state of a qubit instantly influences the state of another regardless of the distance, and this on the one hand facilitates more powerful quantum computers, quantum algorithms, but also enables some kind of like secure communication. And that's basically the backbone of quantum computers. Do recommend listening to that first episode, Quantum 101, to understand that in a bit more detail. And today we'll be talking about what this actually means and how we make this practical in the real world.
Yeah, exactly. And obviously, last time we also touched on the difficulties in making these quantum computers, right? And some of the techniques we have with the superconducting quantum computers. So now we've covered how you make a quantum computer. It makes sense to actually discuss, do we make a quantum computer? What would we actually use them for? So yeah, let's go through some of the big major use cases. So one of the first ones that comes to mind and is talked about a lot is for things like drug discovery, right? So when you're a big pharmaceutical company or something, or a medical research company trying to create new therapeutic drugs, or even just do research for things like cancer treatment drugs and things like that, then you have to do these very computationally heavy molecular simulations, right? You have to model these molecules, you have to see how they interact with one another, you have to do very, very complex things that classical computers really just are not very good at handling. It takes a long time, it's very expensive and computationally inefficient to use classical computers for this. So this is one of those areas that people are very excited about for quantum computing, because with all this increased parallelism, with all this increased computational power, the ability to try many, many different combinations of different states all at the same time to see which drugs might work best and things. That's one of the avenues they think is going to be really good for drug discovery and development in the future, right?
Yeah, so I think I saw some estimates from the big consultants of the world that basically said by 2030 they reckon they can save around 1.3 billion on the molecular simulation and testing in the kind of the way that you just described using quantum computers. You talked about the simulation; these are obviously very complex things. So being able to simulate many states in a more efficient way at the same time is obviously good. So that's a powerful application of quantum computing, but also the testing as well, being able to test how they interact over time. What the longevity of these things are. I know that like the average time right now for to bring a drug to market from conception is like 10 to 15 years, so a really long time. And they estimate that using quantum computers, they can halve that. And a lot of that is basically being able to rapidly test lots of different scenarios kind of simultaneously, whereas like classical computers take a long time to model, say, 100 atom molecule. It might take hours, it might take years, sorry. Whereas quantum computers can obviously do that same mapping and test in hours, theoretically, anyway.
Yeah, and obviously this is a really good thing for the drug companies in particular, whether or not you think that in itself is a good thing, but it's a big business that, and the amount of money that gets put towards these research processes and trials is huge, right? It's a $1 trillion industry, I'm sure. So any way you can save things in the billion, that's going to be very helpful. But I've also seen people talking about how it's very good for the state of clinical testing and trials as well, because being able to do all these much faster, rapid computer simulated testing means that we can rule out certain drugs much faster without needing to go to kind of animal or human trials and things like that. So from an ethical
Mm.
perspective, that's also quite a good, quite a big benefit of this use of quantum computing, I think.
Yeah, healthcare is universal. That's why we kind of always start with it when it comes to applications, because everyone gets it, and being able to lower the cost is obviously good across the world. So another one that's somewhat universal, even if people don't know it, is cryptography, and that's one of the things that we see talked about and discussed when it comes to quantum. A lot of the time is, are these cryptographic algorithms quantum resistant? That's the buzzword. And basically, to say why we say this is kind of applied horizontally across the world is that a lot of the secure communication, a lot of the systems you're using are based on, basic cryptography algorithms that have been around for like, 15, 20 years, basically. RSA is one of the fundamental ones. And one of the high level kind of scary things around quantum computing is that it's going to be able to break these algorithms, these cryptographic algorithms that so many applications and so many security mechanisms are based on. And this is a big scary thing. Like, I think I saw some of the estimates of some of the RSA algorithms that we have right now would take thousands of years for a classical computer to break. Maybe not a supercomputer, but a classical computer. And they can be broken potentially in minutes with these proposed quantum computers that will be ready by like 2030. This is a big scary thing.
Yeah, exactly. And this is one of the implications of, when we covered the history of quantum computing, we spoke about how in the early 90s there were these theoretical algorithms devised to say, well, if you could have a quantum computer based on these quantum states and qubits, then you could, in theory, solve some of these problems. And one of the big ones was the one we mentioned, Peter Shor's algorithm in 1994. And this is the one that actually is this is the one that RSA cryptography is vulnerable to. So that algorithm allows you to, we won't get into all the maths of it, but it essentially allows you to recover the private key of the RSA crypto system. And I actually, when I was researching this, I presumed RSA wasn't used very much anymore because it's so old and we have more advanced crypto systems in use now. But it's actually one of the most widely used public key crypto systems still in use today. So it's used for everything from your internet connections right now. When you see the little TSL, SSL connections, things that are very standard and commonplace, lots of the time RSA is still used for exchanging keys when you're securely connecting to a website. So this is quite worrying that can be broken by quantum, right? And then it's not just RSA that's vulnerable. Also, things like elliptic curve cryptography, which is what's used and is the bedrock for your private keys in Bitcoin. So yeah, it's a bit worrying that both of those systems are vulnerable, especially in the Web3 world, right? When you can maybe have your private keys exposed in that way.
I mean, yeah, it's one of those things. If it ain't broke, don't fix it. So you got a lot of these legacy systems that have been using RSA, which has been around for like what 30, 40 years or something like that. But now we're getting to the stage where it could be breakable. And I think like some of the estimates on if you could actually commercially and practically break RSA on like a global scale, it's like obviously trillions of dollars. Like this is the backbone of the internet in so many ways. Yeah, this is quite scary. So one of the big things we've seen is around the idea of these quantum resistant cryptographic algorithms. I mean, even like just simply you can like compound what's one of the most basic Bitcoin transactions is a pay to public key hash, right? Even just adding a degree of hashing to your cryptographic signature, what might make it more secure. So like you said there that we can use RSA because of the factorization problem that can be done much more efficiently on a quantum computer can be potentially broken in minutes rather than thousands of years. But it don't have the same problem with hashing algorithms. So I think it's like for the hashing space for SHA-256, we're getting to the mathematics a little bit here, right? Is the search space like 2 to the 256, obviously, and a quantum computer right now can only do that in a factor of 2 more efficiently, basically. So it's still a huge space. So even just adding a simple hashing algorithm onto your cryptographic algorithm could solve some of these problems, but that's a bit boring, I imagine, to talk about now.
Yeah, I mean, it is an important distinction to make that a lot of people say, well, quantum computing is going to break things like Bitcoin, and it's right that you distinguish between the elliptic curve cryptography and the algorithms behind that, and things like hashing, because part of the security of Bitcoin and similar things, especially proof of work blockchains, is on the hashing process. We talk about how miners are hashing all the time. And yeah, as far as we know, right now, hashing isn't vulnerable to any quantum algorithm. So no one's come up with a theoretical algorithm that will, make hashes vulnerable, because that would really, mess up the security model of Bitcoin. You wouldn't know what was the correct state of Bitcoin anymore. But it's those key pairs that are potentially vulnerable. So yeah, I think we're going to have to see this shift to quantum resistant schemes or quantum secure crypto schemes. And at some point, all the major blockchains, if they haven't already got them, especially the legacy kind of older chains like Bitcoin, Ethereum are all going to move to these quantum secure algorithms. And, just to highlight how new a thing this is. So NIST, the standards agency in America that is responsible for basically deciding via competitions which is the most secure algorithm, they've actually only just, as of kind of a couple of weeks ago, published their shortlist for quantum resistant cryptography scheme. So this is still not finalized which one is going to be the NIST approved one. But yeah, once it is, I imagine we'll see a lot of people transitioning over their blockchains to that.
Yeah, that's quite exciting. And I think one of the things that I've seen around this as well, and I'm sure we're going to talk on a bit more, is the idea of actually using quantum key distribution as well. So this is a way for secure communication. We talked about entanglement properties a little bit in the Quantum 101, being able to kind of link two qubits so that they can communicate with one another. And if you move one in a certain direction or move another in a certain direction, the state will change, and that creates a way to communicate right across distances. So if we could then actually deploy that same principle to a secure communication channel with potentially private keys similar to Diffie-Hellman style, and someone were to eavesdrop in the middle, we can actually detect, because of what we said earlier, that we don't really want any interference between those two qubits. As soon as there is interference, that connection breaks down, and this could create a secure communication channel as well. So there are some opportunities there related to security in the cryptographic insecurity.
Yeah, you're saying it's not all bad, right? Quantum isn't just here
It's
to
not all
eat our
bad.
blockchains. Yeah, it's
Exactly.
good to know that we can use the same properties not just to attack blockchains, but also to improve security and things. And there's some high profile names already putting this in production. So I think there was a partnership between EY and Toshiba. They launched one of these quantum key distribution QKD networks back in 2022. So that's been live for a number of years now, to improve the security of these cryptographic keys that are the bedrock and underpinning of lots of our secure systems today. So that's a positive thing.
Okay, so to move on to the next one, we've got optimization problems, super general. Let's talk about maybe something that's also general is supply chains. We've done a whole episode on supply chains and how kind of wide-ranging and impactful they are in society. They're worth trillions across the board, super vulnerable, all this kind of stuff. And similar to the molecular stuff for drug discovery, we have lots of variables, and it kind of, the problem scales quite significantly when you think about, how do I get my van from A to B, and how do I get 100 vans from A to B, and then 1,000 different destinations? Like, the problem is huge and vast. So being able to optimize, say, something like supply chains using something like quantum, which is obviously a more efficient way of doing it, could save hundreds of billions a year across the world globally, but also make things more efficient. So one of the projects I saw around this was, I think it was Volkswagen successfully used a quantum computer to reduce real-time traffic in Beijing and save like 5 to 10% of like gas consumption by doing that. So these are actually things that are happening now using quantum computers and are actually making a real-world difference.
Yeah, it's very impressive. And obviously, like, if you're going to talk about optimization problems, it's a general class of things, right? It could be many different things. It could apply to financial markets, trying to optimize the returns on your portfolio or something. But in the logistics industry, that's so complex, and we saw all the issues around COVID when things break down. It's good to know there are applications of quantum computing here, and that's again taking advantage of the superposition properties that we mentioned last week. So being able to run many different trials simultaneously and find the best answer, the optimized answer, very quickly using that superposition property. So that's good. And yeah, I've seen there's lots of people starting to make moves in this area. You've got I think there's a company in Latin America called Quantum South. They're applying this with the International Airlines Group to the whole management of flights and things like that. So workload efficiency gains that they're targeting there, and they're very optimistic about how this could help them reduce kind of inefficiencies and things.
That intentional world puns.
That wasn't
Optimistic about
intentional.
optimization.
I heard it when I said it. I know.
So we try and get two buzzwords in one and talk about artificial intelligence combined with quantum computing, combined with blockchain and crypto and everything else.
Yeah, why not? I mean, artificial intelligence is your favorite thing to talk about, right? Because you live in the AI world now. You use it for all your work, I presume. So yeah, let's jump into that.
I think, like, obviously one of the big things is around the obvious ones around training the models. Like, it takes a vast amount of computational power and time to train these models. Like, you often try and parallelize it. You have hundreds of hours, weeks, if not months sometimes, training these models just on one data set, trying to optimize the output. So again, this is an optimization problem. Being able to do that with a quantum computer is an easy win. Like right now, I've seen that more, well, we had this boom of AI companies everywhere, just basically trying to say, we'll become profitable in 5 years' time. And then they started to realize that as they're scaling up, they have to scale up their back-end servers to kind of do all this AI computation. It's getting more and more. Well, it is expensive right now. We'd hope that the hardware does eventually bring the cost down, but right now it's becoming infeasible for a lot of these companies to do this, and we're kind of getting this centralization in a lot of ways of the AI offerings because it's so computationally difficult to basically optimize these AI algorithms.
Yeah, and I think from my perspective, it's hard to know precisely how they're going to use the quantum algorithms, for me at least, because how the AI models work and are trained are somewhat opaque already. Like they're a little bit behind closed doors. We know some details, but we don't know everything, especially about the data sets they're using. But it is probably the area that is the biggest wing of big data at the minute, right? They are the biggest data centers. These models have billions to trillions of parameters involved in them, so they're incredibly complex machine learning techniques being used. And in theory, yeah, the kind of parallelization properties we talked about last episode on quantum are some of the things I think that can target here. And again, you've got the big names who are working on this. You've got people like IBM. Their quantum team is, developing their own quantum machine learning algorithms. So I presume it's possible. It must be possible, even if I don't quite understand how. And they're at least their early research is showing that this should significantly reduce the time required to do things like training the AI models on those initial data sets and things like that to help, improve predictions we get from them.
And I think like one of the things here that I'm kind of torn between whether I think it is going to be easy to do or difficult to do is that when you think of like the quantum algorithms right now that we've talked about, they're very specific. Like it's very much it's a mathematical problem in a lot of ways. Like you're talking about the factorization of RSA, very simple in a way, I guess, to model like input output what the success criteria is. But when we talk about AI, it's a bit more generic, like it's a bit more ambiguous. So it's harder to maybe simplify it down, but then maybe not so much. At the end of the day, it's all binary, it's all maths running through. Even if we think that the output is very generic and ambiguous, maybe it's not so much. So we'll see how that plays out.
Yeah, and we talk about Shor's algorithm. I think you will start to see more and more algorithms be created for these specific problems. So things like machine learning, like IBM's working on, and you can say, okay, now we have an algorithm that can be used with a quantum computer to attack this problem. And I think that's probably one of the big areas of research you have on the side of building the quantum computers and how to do it practically, and also on what algorithms can we use now that we weren't able to think up with classical computing. So yeah, on that note, then why don't we talk about some of the actual kind of societal impacts of all this, right? We talked about some of the ways you can use quantum computers, the problems you can solve, but what's it actually going to mean for society? So we've already said, I mean, naturally, this is going to touch virtually every industry, much like AI. It's a very general potential solution to lots of different problems. We talked about logistics, finance, healthcare, all these things already. So we know it's going to have a massive impact. I guess we just don't know quite where it will have the most impact yet, right?
Yeah, I think like one that I can think of off the bat, which is kind of happening with AI in some ways right now, and we've kind of touched on it a little bit, is the people that can run these quantum computers are only going to be governments and super huge entities, right? And this, in my mind, is going to create a centralization of power to an extent. Like, if your classical computer or classical computing system and servers and all this kind of stuff can no longer compete with, say, the one supercomputer or quantum computer that's working in America, like it's just going to be able to optimize problems in seconds that would take you years and then just outperform everyone. So I do worry it's going to lead to a centralization of power in some ways, but maybe we can get around that using blockchain or something like this.
Wow, wishful thinking, blockchain, the solution looking for a problem. Um,
Yeah.
yeah, I think that's something maybe, I mean, it was implied when we last spoke about quantum, but because of the practical difficulties in creating these quantum systems that you build the computers from, it seems very, very, very unlikely that we will ever, even with Moore's law and things factored into all this, that we'll ever have practical, commercial, kind of retail end user quantum computers. They'll probably always be in the Googles, the Apples, the IBMs of the world in these massive data centers, carefully managed and things like that. And we'll all just be probably accessing them from cloud services. So that there are some cloud services that exist already. I think that you can make requests to. So like to Google's one of Google's prototype in beta machines, I think one of their computers, you can interact with it by sending requests. But at the end of the day, they're still hosting the whole thing.
Mm.
They're mediating the response. So when we talked about AI just now and saying, well, there's a centralization problem there. Will quantum computing help it if it's just in these massive same group of Silicon Valley companies who hold the quantum computers? Yeah, I don't know so much. That is one of the big risks, I think. And we've got a
I've seen
space
that.
race on, right, as we said. So
Yeah, on that idea of like democratization of quantum, like you democratize access to IBMs. Say, okay, it'll take you 10 years to train your algorithm. I'll charge you 20 million, and it'll take me 5 seconds to do it on my quantum. Here's the API to do that. And I guess that makes sense when it's a non-competitor, but it's like kind of similar to the Amazon style, where as soon as they can undercut someone on their platform, they will. Like they're only going to allow that for non-competitors to do that, right?
mm.
But yeah, let's see. I think let's to move on to the next one. Obviously, there's going to be a job market shift because of this. There's going to be more Jack Davises of the world playing with their Johnson Johnsons, throwing electrons through insulators, taking weeks and millions of pounds worth of helium. That's going to be. I saw that they said it might create over 200,000 new jobs. I think by like 2035, something like this. So it's a big business.
Yeah, so everyone who lost their job from AI can then just become a quantum computer programmer, right? So, no, yeah, it's going to be interesting, like because obviously it will be an extremely specialized field, but for those in it, I think that will be one of the new like top tier jobs to be in, right? To be in the development of these quantum algorithms, to be people who can configure the computers. It's going to create lots of jobs in manufacturing as well, right? Because of all the materials needed to create them, and as this space race continues, there'll be more and more money put into it. Like
Mm.
the US government has already invested well over $1 billion into quantum initiatives, as I understand it. So yeah, the job market, as with all of these new emerging technologies, will definitely have some kind of impact. But will it replace all the AI jobs? Who knows? Like that's the open question.
Yeah, that the what's it called? The US investing what 1.2 billion into what's it called? The National Quantum Initiative Act. I guess that's kind of there's a double-edged sword there. One is it's to be world leaders, pushing the boundary of quantum, blah, 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 all this kind of stuff. But I imagine also it's going to be a lot of consultants coming in and being like, okay, these are all the vulnerabilities you have in your system. You need to update all this, or potential foreign enemy state is going to hack you with their quantum tech. So I imagine there's going to be a lot of updating legacy systems to make sure that their current systems are safe and secure as well.
Yeah, it's a bit reminds me of the Millennium Bug, right? And the fact that there was a whole
Mm.
worldwide surge to update our legacy systems so that planes didn't fall out of the sky on the first day of the new millennium. And that is going to be a genuine risk if these quantum computers can support more and more qubits, can break things like RSA, ECC. Because every system that uses that will need to do that managed upgrade, and even though with NIST rolling out its new algorithms, it will people are not too worried about it happening, but there's still a huge amount of work to do to transition the legacy systems over that will cost a lot in the short term, but it's just one of those necessary things now.
Yeah, I think like overall on like the job market economic disruption piece, it kind of doesn't seem too fundamental a shift. I guess we can kind of think of it as just like an improvement in computing power, which has been happening anyway, right? It's not like it's going to completely overhaul the whole job sector. It's probably just going to make certain sectors where it's applied more productive, have better outputs, that kind of stuff, and there'll just be more people moving from legacy style hardware to supporting this quantum style hardware. So it doesn't really worry me as much as say things like AI, where it's kind of like there's a
Yeah.
jump from the capabilities of what can be done and the understanding of what can be done basically over the course of a year, which is revolutionary.
Yeah, exactly. And the AI explosion, there's a lot more of the unknown about that, I feel, than with quantum, where you need to come up with the algorithms to break certain things or improve certain things. It seems a little bit more step by step, whereas AI is kind of this beast that's growing and growing with more data and getting out of control. And yeah, speaking of AI, then because we want to situate this in the world of Web3 as well. And have always treated Web3 as a broad church of different emerging technologies. I think quantum computing is probably the first technology that is fairly orthogonal to most of Web3 in general. Like, it's not necessarily directly overlapping, but it's kind of growing in the corner. And we've already spoken about, okay, all the blockchains are going to have to think about this, at least, whether that's I think Deloitte estimated 25% of existing blockchains are going to have to make upgrades because they have vulnerabilities. And if something ever happens and someone comes up with an algorithm that breaks hash functions, that's a whole different problem. But aside from just updating the crypto systems for the key pairs and things, what do you think are the big impacts for the rest of Web3, right? Like opportunities or risks that come with it?
I think like we kind of touched on it a bit earlier, so I'll just briefly mention it again. The idea of potentially democratizing access and tokenizing quantum resources, like it's going to be a big fear factor. Say having 5 companies or states around the world that have access to these quantum computers that are so much more powerful than everything else in the market. So all of a sudden, people, they might want to democratize that. They might want to allow anyone to have access to that for a certain price, and then say, I will pay for X amount of time or X amount of compute power to solve this problem. Being able to do that with kind of a peer-to-peer decentralized network might be the most efficient way to do that, to represent ownership, represent access. That's one thing I could think of.
Yeah, I think that's the main one for me as well, right? Like the tokenization of access to the resources, being able to use things like micropayments again, in the same way we describe for AI, like for very small, simple tasks that are massively sped up by quantum computing, in the same way as you can get those done with AI. And we are starting to see AI and people talking about AI agents empowered with the crypto wallets, like we've been talking about. I think the whole tokenization and micropayments model for quantum computing will be maybe in 5-10 years, when the quantum computers are big enough that they can support hundreds of millions of users concurrently requesting things. And then you want those requests to be a very small payment attached. You don't want to pay £10 every time you call it. You want to pay a penny or something like that. So I think that is probably the main area. I kind of struggle to think of what the other overlaps will be right now. Because the idea in blockchain of lots of people wanting blockchains to be heavily decentralized and being able to run those nodes and things at home or be part of the network, and to add quantum computing into that infrastructure as blockchains. Most blockchains, like BTC, they
Mhm.
are not compatible with the idea of quantum computing being these big, heavy, resource intensive things that you can't run at home. So I think, some blockchains may end up being run by quantum computers. Who knows? But I don't necessarily
Mhm.
see that in the near to midterm future for me.
Yeah, I'm kind of thinking of it like Sauron's eye right now. There's going to be 5 Sauron's eyes, and wherever they put their focus, that thing is going to change radically. And because there's only 5, and they're going to be massive companies in big states, like they're going to focus on maybe the big topics at hand, whatever it is: sustainability, development, optimizing logistics, that kind of boring traditional Web2 stuff, right? I don't see their focus being blockchain, the cryptos of the world for the next 10, 15 years. But you said that could change quite quickly. Like if all of a sudden they can commercialize it much faster and parallelize the development of this stuff, then it might change. And I think, yeah, one of the crazy things that we have to get our head around is that it's not just, say, a Bitcoin system of the world today could say, we're going to change our key pair system or cryptographic signing system from today. They have to backdate everything, right? They have to backdate all the network, all of these whales that haven't touched their keys for like 20 years, maybe even Satoshi wallet, whatever it is. Like that has to be backdated as well. And that's a huge task. Like it's a huge problem. Maybe not so much for BTCs because there's not, what hundreds of billions of transactions, but for some of the networks that have really high throughput, you have to change that stuff.
Yeah, you're right. That I think the migration problem for blockchains is probably much worse than in the Web2 world in that respect, because you have to get you have to communicate this new thing to everyone. You have to say we need to migrate keys and things. You need lots of on-chain transactions to do that as well, to move funds from one to another potentially. And again, I don't know exactly how people are planning to transition. I think that I haven't seen many kind of active plans to transition things like Ethereum. Yeah, I might be wrong on that. But yeah, one thing you just made me think of as well is all these keys that people have lost over the years, right? We talked about the guy in Newport in South Wales
Oh
who's lost
wow.
his hard
Yeah.
drive. Maybe there'll be a service in that in the future for ethical hacking of old wallets, but then there'll be a whole bunch of other issues around that about proving that you did own it and stuff like that. So yeah, I
Oh my
think that'll
God,
be
that is
interesting.
bonkers. Yeah. And that is absolutely crazy to think of that guy who's got like 200 million Bitcoins lying around, some quantum service being, I'll find your keys for you. Here you go. Just give me half. That is mad. And like you're saying, like blockchain data is notoriously very unstructured and very indexed, like very good for verification, but very difficult to actually search through. So this is going to be a huge, huge task to actually like, make this tabular, make this easy to read through. And like notoriously people that are using crypto want anonymity, don't necessarily want to be communicated with, and like the idea of them being potentially doxxed by having to talk to an exchange and update everything, like there's so many problems with this kind of stuff. It's actually quite
Yeah.
scary to think about what the implications are going to be.
You're right. I'm actually a bit more worried now that we've kind of spoken about it and reasoned it out than I was half an hour ago. Yeah, and I
It's
just a
like
final
your
thought
£5 in Bitcoin will be safe. Don't worry.
if that. Um, yeah, maybe as a final thought on the Web3 stuff as well, I think it will also depend on what, moods can change in the philosophical interpretation of blockchain as well. So I just mentioned that it's incompatible, this quantum computing idea of big, heavy systems working with heavy decentralization, where you want everything being run by the edges. But maybe in the future, we know Bitcoin and things like that are run by a small number of players in effect anyway. So what if they do start saying, well, actually, we can do this much more efficiently with quantum computing, we can validate transactions
Mm,
more efficiently, we can offer data services, you can put data on chain more easily and more inexpensively. So maybe eventually there will be a shift in the narratives around things like Bitcoin, but I think that's still
yeah.
also a long way off.
Yeah, like really quickly on that point, like optimizing supply chains, optimizing, traffic, all this kind of stuff can apply to networks in the exact same way to being able to optimize transaction propagation, all this kind of stuff. So that kind of boring, but it can optimize, Bitcoin, Ethereum, all these kind of things. Another interesting point that's probably a highlight is like you kind of said that this stuff still doesn't solve the hashing problem necessarily. This quantum doesn't get around hashing. So maybe Bitcoin, Ethereums of the world might suddenly have much more value, maybe even more from like the proof of work perspective, where these quantum computers still won't be able to get around the proof of work to say, okay, well, what is one of the merits of Bitcoin? It's the fact that it timestamps based on this enormous amount of work, so you know what the series of events happened in this chronological order, right? And that's quite a powerful thing. When we think of like traditional Web2 style legacy systems, you get these, basically the record of events is done by a notary or a signature, like a trusted entity based on RSA. The timestamp doesn't necessarily come into it, but you kind of trust their timestamp. So if I could break into that, get the key using a quantum, and then change the entire course of history and just timestamp it with whatever I want, it suddenly becomes difficult to work out what the order of events are. But Bitcoin still has this this way of defining what the order of events are based on this enormous amount of work that goes into it. So maybe there will be a place for proof of work style blockchains in the future once they can get around this kind of ECDSA problem we talked about.
Yeah, exactly. I think it's to summarize, it's kind of Bitcoin has this unique value proposition in my mind, and proof of work in general has a unique value proposition over other consensus algorithms potentially. That way it has this property that it's very difficult to forge the history, and it's good that as of now, quantum computing doesn't seem like it's going to change that. So it's basically saying proof of work blockchains haven't lost this yet. If someone comes out with an algorithm that breaks that, that might be something that Bitcoin and proof of work blockchains have to lose, right? That would kind of potentially almost level the playing field between
Mm.
uh, Bitcoin and other blockchains. Then, because well, you can say, well, if it's easy to create an alternate history of Bitcoin using these quantum computers, then it almost loses the benefit of proof of work. And that whole argument about why we need proof of work might end up, having fewer legs to stand on in the future. But yeah, it's an interesting thought, and hopefully it doesn't come to pass. Hopefully no one comes up with that algorithm. But yeah, we'll see.
The question is, how likely is it? We're saying that there are some quantum computers that exist right now. We've talked about some examples of how they've been used already, but are these things going to become commercial? Are they going to become like part of our day-to-day lives?
Yeah, I think, as we said, not part of our day-to-day lives in terms of us running them, but I think there has been so much progress. And you take a year off from looking at these things, and the number of qubits, which is basically the main metric that people are interested in, about how many qubits can you have in a quantum computer and how long can you keep them in these entangled states for, right, without them collapsing and decohering, as you mentioned. So, some of the records, and you can see the growth here. So in 2019, when we mentioned Google said it first achieved quantum supremacy, so it can beat a classical computer at a given task, at that time, the record was 54 qubits that Google had. And then as of December 2023, IBM got to 1,121 qubits. And just for context,
Whoa.
you need something like 2,500 qubits to break elliptic curve cryptography for the kind of key lengths that we currently use. So it's gone from 54 to 1,121. And currently the record is around, just slightly more than that. It's just under 1,200 qubits. So it's increasing all the time. I don't know if it's plateauing or anything, but it seems like for these big companies that are going to be running the quantum computers, it's getting more practical all the time. Who knows how far off we are from them, being large scale commercial that we can all access through APIs and things. But it does seem like
Yeah.
the march is onward in these things.
And one of the interesting things about this is that because it's probabilistic, because like it's not definitive in a way, like actually one of the reasons you want to scale and have lots of qubits is for error correction. So you might have, if you only have like a system of 50 and say, 40 of them point one way and 10 of them point a different way, like the more you scale this up, the more, likely is the probability gets to the right value, right? So when we're talking about, I've seen like numbers thrown around that when you actually need systems in the order of millions of qubits to create, quite importantly, reliable large-scale quantum computing, which is the key, is that it's reliability. A lot of these things are still very error-prone, and they won't always optimize to the right value. And like the amount of money that's actually going into this, I've seen like it's like 25 billion a year globally is going into quantum R&D, which is an R&D budget is just astronomical.
Yeah, and that's funny because like when I've seen predictions, obviously these predictions are always crazy and can be very inaccurate, but the industry size was something like only 1.6 billion in 2022 estimated, and then they thought it'll be around 50 billion by 2035, and already those kind of budgets you're mentioning were already hitting the 25 billion spend per year. So yeah, it's crazy. And the one thing I would say to caveat, okay, we're increasing the number of qubits, but as you said, how long are they being kept in this state? How long are they being kept, in a coherent state and usable as quantum computers? Because that's the bit we don't necessarily know. Are they getting 1,000 qubits together for half a second? Well, that's not that useful. Are they getting them together and keeping them there for days or weeks at a time, which is much more useful? So, yeah, it's those two different things you've got to measure. It's back to Heisenberg's uncertainty principle. The more you know about one, the less you know about the other. So.
And just to end with some probabilities, I saw a study that said 50% of quantum computing experts believe that it might be possible in 10 to 15 years. Probabilities within might.
Yeah, well, I mean, I was going to end with the joke that we've probably got Schrodinger's viewer right now, Schrodinger's listener. We both have one and don't have one until we put this episode out. So yeah, it's nice that we're in that state where we could have one, but I'm doubtful.
And on that bombshell, well, I hope you enjoyed this practical applications or somewhat practical applications of quantum computing. We basically covered what it might mean for the world when these things get deployed at scale. But yeah, I hope you learned something. And thank you for listening, wherever you may be, and join us next time to untangle a little more of Web3. Thanks for tuning in to another episode of Untangling Web3.
Don't forget to send us your thoughts, questions, and comments on social media. And be sure to follow us on your favourite podcast provider to catch the next episode. See you next time to untangle a little bit more of Web3.
The views we express here are our own and do not reflect the views of our employers.